So, before we get into the details of the chart and all that kind of stuff, any questions from homework, first thing? I still ask that question. I'm so optimistic. I'll never give that up. What? Okay. I'll never learn my lesson, but too bad for me. So, I want to talk a little bit about, I want to remind you where we've been already and where we're about to go. The normal distribution. I think I flashed up there the actual formula for it once. I can't remember, it had an e to the negative x squared with sigmas and mu's and all that stuff running around. Really funky ass formula. We didn't use it directly. I told you that's what governed the shape of it. It was just like plot. If you put that into your calculator, it would actually plot a normal distribution. So there's a normal distribution that exists. It's got its own little function that describes it, right? It just exists on its own. It's actually related to what's called a Gaussian distribution, because there's a guy named Gauss who just did way too much shit. It's like, dude, let somebody else do something. Gauss was involved in a lot. All right, so if you want to look up Gauss, if you're like really bored or actually interested, look up good old Gauss and see what he did. That's what we measure strength of magnetic field in, is Gauss. Okay, so we have a function that's really kind of ugly that describes this. But how did we use this? How did we use this distribution? What formulas did we actually calculate to plot on this shape? It wasn't the function they gave us. It was z-score formula, right? So there's how many? I always say there's one z-score formula. There's one like form for it, but there were several types of forms of it, right? There's that one, and there was like this thing, right? All this, right? Is that decent? You guys with me? So there's a shape that exists, a probability distribution that exists, and there's multiple ways of identifying places on it. Okay, I like it. Now, chi-square is sort of the same way. And this distribution is how certain things are distributed. So like heights and weights and scores for things and so forth, like IQ scores and all that kind of stuff. IQ scores are forced to follow it, but oh well, they do, obviously. And I talked a little bit about last time how the standard deviation actually governs how fat or skinny this thing is, right? So the standard deviation, if I wanted to see how standard deviations are distributed themselves, I obviously can't use this. Because it's supposed to have a standard deviation that tells me how this thing is shaped. So hopefully that part makes sense. So there's a sort of a different distribution. I'm not going to get too much. I think I said this last time. If you fold the z-score distribution on itself, you get the base chi-square. But most of these look somewhat like this. I think I called it the Job of the Hut distribution last time. That's what I think of when I see, big body, little tail out there. Oh. No. No Star Wars. No. Oh, it's sort of okay. So this thing is its own shape. It's got its own formula. The formula is based on the sample size, which kind of makes sense because this is going to deal with. This deals with, for example, this could deal with how a single data point lives within all of the data points. Where is it relative to the other data points, that kind of thing, right? So where's your test score relative to everybody else's test score? How's that? Is that a decent? You're all like, continue. Okay. This could talk about how does this fall amongst all the possible those, for example. Sort of similar idea. So this would be like for data point, this would be if I took a sample and got its standard deviation. How does it compare to all the possible standard deviations of all possible samples of size n? So the shape is going to change for how big n is. So we're going to have a table that's based on degrees of freedom. Did I give you guys the table already? All right, good. So you can see there's degrees of freedom right there. Yes, ma'am. Oh, sure. Where did I put the rest of them? There they are, Jeff.
Yes, looking at the final exam questions.
Well, you did, didn't you?
Do you need that too?
Yes, please.
All right. So there would be several kind of formulas for calculating score that would fall on this. So, for example, let's see if I remember the one for this guy. If I was talking about how standard deviations of samples fall based on the standard deviation of the whole population. Right? So again, what is this? Let's go back to what we know. What is mu? There you go. Cool. The mean of the population. And what was x? A single data point. I love it. Kick ass. So that talks about how a single data point relates to the average of all the data points. Right? This would be how a single sample's mean relates to the average of all the sample means. Right? So here, I could take a sample and get a standard deviation, and I want to know how does that relate to all the other possible sample standard deviations. So the formula here would look like this. This is very different than what we're used to, obviously. But so that would be one possible chi-square. You would use that chi-square formula to create confidence intervals. So I could take a sample standard deviation. I can get a sample standard deviation. Is that going to be the real standard deviation for the population? If I take a sample and I get an S, I would put money on it not being quite the right sigma. It could be really far off, but it's more than likely off. So I can make a confidence interval for where the real standard deviation might be contained within this interval. Are you guys semi with me a little bit? So just like I use z-scores to create confidence intervals for means, I could use these chi-square scores to create confidence intervals for standard deviations. All right. Now the one we're going to focus on, because we only have so much time, namely today, is we're going to focus on the goodness of fit formula. I don't think I'm going to write it up here yet because it's got to deal with something. We got to look at the little chart to see how the formula makes sense. This is what I really wanted you guys to understand is, at this point, if you're not really decently comfortable with this, not much more I could do for you. I'm hoping if you're decently comfortable with this, you can see some of the analogies between how I use this to talk about where data points fall, and I could use this to talk about where sample standard deviations fall relative to everybody else. So where's most standard deviations fall? They would fall in here. And there would be very few out there, and very few back there. Okay. And it's not symmetric, it's just too bad for it. Okay. All right. So let's look at what we're going to focus on. So that's one way. The formula we're going to focus on is actually on that handout I already gave you. So let's look at that sucker. Let's make some sense out of it. So, for example, what was the example? Oh, yeah, M&M's. Blood cholesterol. Let's see, what else can I do? Grades, sure. I think I did grades on the praxis fund. Well, sorry. So let's say I thought grades should be, this would be silly, but if I thought they had to be uniformly distributed, meaning there should be equal number of A's, B's, C's, D's, F's. Kind of a silly expectation, but let's say that that's the claim. Some crazy person is claiming. Right? We're going to show they're wrong. So let's say that there are 40 students in a class. If the grades are evenly distributed, uniformly distributed, how many of each should there be? expected versus observed. So what's expected then? If I think that they're uniformly distributed, yeah. Say again? 8. There should be 8 A's. How did I get that? 48 students divided by 5 possible grades mean there would be 8 in each category. So how many categories are there? 5. That's going to be important in a second. So one possibility is that they say we think it's uniformly distributed, which makes sense for something like M&M's, colors, right? You would think that they'd be uniformly distributed. Maybe they're not. Yeah, I like it. There always seems to be fewer of the colors you like when you're a little kid. Oh, green, there's only one. Oh, shit. I just want to see the little kid go, shit. All right, so there should be 8. I expect there to be 8 in each. Based on how I feel, I expect there to be 8 each. Doesn't this add up to 40 students? Of course, 8 times 5 is 40. I like it. So part of this is going to be figuring out, based on what the claim is, or what the feeling is, how many should be in each category then. Because these uniformly, you just divide how many by the number of categories. Everybody gets the same amount. Okay, so this is one way this could be set up. Now let's say, I'm going to put in purple what I've got to kind of tell you. Let's say I actually observe, out of these 40 students, I see 10 A's, 11 B's, what you got, Jeff? 5 C's, 4 D's, and 10 F's. Thankfully, that adds up to be 40. Okay. Now, I really want this to feel very similar to what we've done already. Can you categorically tell me right now that this is not evidence that all grades are uniformly distributed? This is just 40 students, right? It's not all possible students for whatever I'm talking about, all stat students or whatever. Are you guys with me? So the same way, please don't freak out when I say this phrase, because this is not going to be all the steps of this, but the same way as a hypothesis test, where the sample has to be so far away from the expected that, shit, it can't be right. That's the idea with the hypothesis test, right? The same thing's going to happen here. Now, if this was perfectly uniformly distributed, obviously these should all be 8. So obviously all the distances between these would add up to be 0, right? So here's what we do. This actually feels a little bit like doing a standard deviation in a way. What do I get when I do, let me do it the same way they do. What do I have? There, okay. You'll see why it doesn't really matter which way these are, but it just depends on the book. Observed minus expected. So what's observed minus expected for each row? This would be 2. 3. Negative 3. Negative 4. 2. I like it. And notice what these add up to be. 0. I like it. That makes sense because they have to be, as many as are above this, there have to be an equal kind of amount of values below that. And overall, it's got to come out to be 0. So what do? We do the same thing we did back in the day when we're doing standard deviation. So this is kind of like, how much does it deviate from what I expected? That's always going to add up to 0, so that's not very useful. So I square those. So you get 4, 9, 9, 16, 4. Okay. And then my chi-square formula, just to give you a target, it's on that page there. I need one more column. Because now what do I want to do? I want to sum up those. Do I have those yet? Nope. So I got to divide each piece by the expected. It's kind of like the percentage of the expected that's there. The divide by the expected is the percentage of the expected that the difference is. Okay, so if I do 4 divided by 8, I get 0.5. So 4 divided by 8, is everybody with me? You can imagine how the lists in the calculator could help you with this, right? So it'd be 4 over 8, 0.5, 9 over 8, 1.125, 9 over 8, 1.125, 16 over 8, 2, and then 4 over 8 again, 0.5. So then I get 1, 3.25, 5.25 maybe? You guys just gonna trust me? .25, 4.25, 5.25, yes. This is equivalent to step 4 of the hypothesis test. How far was our sample from what we expected it to be? So this is sort of like our Z star in a way. Okay, now we need to see. Okay, so that's not 0. We knew it wasn't going to be 0 because these suckers aren't exactly this. But now I kind of see how far away relative it is. Now I have to see what number to compare that to. So the beautiful thing about this distribution is if it was perfectly 8, 8, 8, 8, 8, this would have come out to be 0. And that's the smallest it could possibly be. Do you guys agree? Because it's squared, right? So the smallest this could come out to be is 0. It can't be negative. And that's where this thing starts, is at 0. So I'm trying to show that the sucker is so far away. If it falls way out here, that's evidence that it's different. It's just a sample. So if it's here or here or here, that could just be random variation. It could be okay. Same ideas with the hypothesis test. Does it have to be exactly the same as the expected mean? No, it could be a little bit off because there's going to be random variations in your samples. So your sample's got to be so freaking far off that what's more likely is that it actually is in the wrong place, that middle. So the next step now is, how do we tell what far enough away is? So in other words, how do we read this crazy-ass chart? So let's focus on that. Everybody's got a crazy-ass chart, right? It's a new crazy-ass chart, by the way. You're all like, I have several crazy-ass charts you give me this semester. Okay. So, degrees of freedom for a goodness of fit test. They don't give a crap about this. All they care about is the number of categories. Right? So, in fact, at the very bottom of the chart, it tells you goodness of fit with k categories, the degrees of freedom is k minus 1. So how many degrees of freedom are there for this problem? 4. There's 5 categories, so there's 4 degrees of freedom. I like it. Degrees of freedom. Alright, so let's talk, before I give you the alpha that I want to use, let's talk about some of the evilness of this. Right, now that we're so used to areas being below the z-score I look up, look at the top of the page, it says this is the area to the right of the critical value. Oh, come on. You buttheads. Oh well, too bad for us. So if I wanted alpha, since I didn't really say, what would we have to assume anyway? What's the most used alpha? 0.5. So say alpha is 0.5. So I need to figure out what this critical score is here. A little C for critical. Right? So my degrees of freedom is 4. I want to be so far away. Now, real quick, the reason they set this up like this is if I wanted to make a confidence interval, I would have a lower chi-square and an upper chi-square. I could make a confidence interval then. Wouldn't be as easy as z-scores because there's no negative and positive chi-square shit. It's not symmetric. You have to look both of them up, right? That's why it's kind of set up the way it is. But I want alpha to be 0.05. And my degrees of freedom is 4. So what score do I get? 9.488. So the critical chi-square is 9.488. So did we make it far enough away to show evidence that they're different? We only made it how far away? 5.25. So our chi-square that we calculated was 5.25. That falls like right about there. Not far enough away. So remember, what did 0 mean? 0 would mean that the expected and what we saw were exactly the same. So anything that's bigger than 0 means that's how far off they are. Were these two things far off enough to be evidence that grades are not uniformly distributed? No, they weren't. I only got 5.25 away from perfectly the same. I had to be at least 9.488 away from perfectly the same. I love you guys. You all look at me like, why? Okay. I mean, doesn't it feel, I'm only going to make you do these 2 steps because I've made you do enough hypothesis tests in your time here, right? So this is what I said was the heart of any hypothesis test. How far away do I have to get, and how far away did I get? So did we find evidence to show that grades are not uniformly distributed? No, we didn't. We cannot say that grades are not uniformly distributed. I know my English colleagues are like, double negative. We can't say for sure that they are. Do you think that grades are uniformly distributed? Hell no, right? Do you think sometimes they could be for certain groups of people? Sure, why not? But in general, no. Okay? So, all you have to be able to do is plug the stuff in this formula correctly, meaning really set this up correctly, and be able to use a chart to get this number so you can compare it. So I want you guys to go ahead and try to do, on side 2 of the sheet, those 2 problems. One of them is uniform distribution, if I remember. Oh, this is an example. So there's only one problem for you guys to do. There's an example of uniform distribution at the top. I want to see if you guys can tease out what to do about number 2. You need one of these? Okay. This is the one that had the correlation thing we did last time on the other side? Sure. Okay.